Hello everyone, welcome to the first lecture of week 11 of the course Power Network Analysis. In this discussion, we will be discussing about certain protection related challenges that come up due to integration of renewable energy resources, specifically inverter based renewable energy resources like solar PV, wind generation, battery energy storage system, etc. What challenges do these renewable based resources, specifically with inverter in between or some converter in between the device as well as the power network, AC power network, what challenges do come up that we will discuss in today's discussion. And this discussion is going to be the last discussion on the module fault analysis. Although, given the time that we have, if one wants to discuss about these protection challenges, one could discuss for hours. But given the limited period of time that we have and the importance of understanding what issues do these renewable energy resources bring in while integrating them with the power network. Obviously, the reason for their integration is that these are green energy resources. They are non-conventional energy resources, not based on fossil fuel, which sort of create their own economic impact, environmental impact. So to limit the discussion, I'll be expanding on three bullet points to given the importance of discussion that we have. I'll be emphasizing on the impact of renewable energy resource integration on short circuit capacity evaluation, also sometimes known as short circuit ratio, and the impact that this integration will have on the SCC or SCR of the overall network will create difficulty in finding the relay or the circuit breaker settings. Remember, when we started with fault analysis discussion, we sort of understood that SCC or SCR, it dictates the ratings of the protective devices, specifically breakers and isolators. And if these renewable energy resources are integrated, the short circuit ratio and capacity, they don't remain fixed because these are renewable energy resources. So their generation would depend on availability of solar and wind. So basically, these have variable injections. If these have variable injections, it's likely that the SCC and SCR will be varying as per the injection available. And then the question comes is, what should be the specific setting given to the circuit breaker or relay for which it should be designed to protect the system against these disastrous faults that we have discussed. That would be one point of discussion. The other point of discussion would be uh, understanding the importance or issues of renewable energy integration on HV networks, what typical relay philosophies are used for protecting high voltage transmission network, and similarly certain issues that come in while protecting low voltage distribution networks, and what could be the typical resolution for these issues in terms of the protection challenges. That's what we will discuss in today's discussion. The last discussion, we discussed at length on certain few solved examples which sort of emphasize the importance or clearly sort of establish the importance of using Fortescue's theorem and Thevenin's theorem for analyzing balanced high voltage transmission faults, that the different types of faults that could occur, and what could be the corresponding current contributions evaluations using the bus impedance matrix, admittance matrix. So I hope the examples were clear enough for the sake of understanding. So coming to our main topic of today's discussion is that if we compare the typical conventional generating devices, which are mostly synchronous generator based devices, and compare them with the renewable based devices. So there is a clear segregation between the quantum of current that these generators can generate. So typical conventional thermal plant or hydro-based plant, which are basically having a synchronous generator or several synchronous generator operating in parallel, During a fault, the typical current contribution is almost 5 to 10 times of normal rated load current or fault current, normal rated load current. And the reason for this increase in current, which is quite significant, is because of the internal dynamics or behavior of, or not behavior, but the variation in the transient reactance, subtransient reactance, synchronous reactance of the synchronous generator during a fault event. So basically what I'm trying to sort of say is that the fault current contribution by conventional synchronous based generators is significantly higher compared to normal load current. And if we talk about similar current contribution from renewable based resources which have some inverter or converter present in between, the diagram here shows essentially a typical arrangement of how the renewable energy resources, often called as distributed energy resources, how these are integrated. So if we have, let's say, a wind turbine, mostly a induction generator based device, or if we have solar PV, fuel cell, battery energy storage system, which are usually DC based devices. So typically wind generation, it is inherently AC, not at synchronous frequency, whereas the other resources, they are inherently generating DC supply or DC power. These devices, when they are being integrated because of their good environmental impacts, they cannot be directly integrated to the utility grid or the high voltage transmission network. There is a need of this power electronic based interface, which consists of rectifiers, inverters, converters, boosting of voltage, etc., etc. And these rectifiers and inverters, they inherently have certain protective functions. Specifically, if we talk about an inverter or a rectifier, the switches which are used in these devices to sort of regulate the voltage level or regulate the sort of generation frequency, these devices, these switches inherently have certain overcurrent rating capacity philosophy, which sort of entails that if some fault occurs on the generation side or on the grid side, then these inverters and rectifiers, they will stop operating. They will stop responding to such changes because of their own inherent protective functions inbuilt in the switches, the sensors that exist. And that is one aspect. That means there is an inherent protective function involved in the inverter based resources. The other aspect is because of these converters and inverters, the fault current level is not significantly high compared to synchronous generator or conventional generator resources. It is capped to 1.2 to 2 times of the typical normal rated load current from the renewable based resources which have inverter in between, due to their inherent control philosophy and partly because of the inherent protection scheme that they have. So the question comes is, why do we need to have these power electronic interfaces when we are integrating renewable resources? The typical answer to that lies in the fact that from the DC sources, which are solar PV or battery and energy storage system, it's a DC based device. So if we have to integrate it to a AC network, we would definitely need an inverter, so DC to AC inverter. Probably this may also have certain other boost or buck boost converters which sort of enhance the voltage level. So typically, let's say solar PV, if it is generating at few tens or 20s or hundreds of volts, and the same voltage level, if it is need to be scaled up to 400 kV, 765 kV, typically direct integration doesn't happen. It all happens to different levels of voltages. So there is definitely a need that, suppose the DC source is being generated at 400 volt, and if we want to integrate it to, let's say, subtransmission level 33 kV or 66 kV, then definitely there is some need of an inverter with some boost up capacity of the voltage. So that is where the necessity of interface of or inverter comes in. That's about DC sources. The question then still remains, why do we need an interface for wind generator, which is inherently AC in nature? The issue with wind turbine or wind generation is that it is not usually generated at 50 hertz. So in order to match the frequency on the DC on the AC side of the wind turbine as well as the AC side on the utility grid, we need to have a conversion mechanism which sort of enables synchronizing or connecting two non-synchronous devices, where here the frequency is not 50 hertz, whereas here the frequency is 50 hertz. So that's where we need a AC-DC converter or a DC-AC converter, again with voltage boost up or boost down capacities present if required. So that's the essence of having this powertronic interface, which sort of limits the fault current. And then also there is an aspect known as FRT, which in full is called as fault ride-through capability. Fault ride-through capability. Also in literature, it is analogously termed as LVRT, which also stands for low voltage ride-through capability. So what does this LVRT or FRT mean? Because of the inherent protection scheme present enabled in the inverters or converters, if the inverter doesn't have this fault ride-through capability, what it would do, the red line here shows that particular fault characteristic or current characteristic that would be observed. After a fault has occurred, the current tends to go up, which is typically 1 to 2 times of the normal load current, and then without ride-through capability, the inverter doesn't respond, it doesn't contribute anything to the fault. Now, why it is necessary to have FRT or LVRT? So basically, what is FRT or LVRT? Given the limited time that we have, FRT or LVRT refers to the mechanism of a generator still being connected to the power network while it is experiencing a fault. And this ride-through capability is important to sort of still support the system without going into a unstable or a blackout condition. Eventually, if the faults persist, the system will experience a blackout condition, but at least only the non-healthy part of the network remain isolated. The healthy parts should still continue supplying the load, still continue operating even during voltage sag or swell conditions, and that is what is the essence behind FRT or LVRT. So basically, it is all about sustaining the fault during the fault while the fault has occurred by a typical synchronous generator or renewable based resources. The blue line phenomena of synchronous generator, we have very well understood that in the previous few lectures, and the red line of the response of inverter is an undesirable response, because if all inverters start not responding to the fault conditions and stop reciprocating, then unnecessarily some healthy load of the part of the network will get isolated, and that may create troublesome. So the green characteristic, inverter with FRT, is desired attribute of the particular inverter, so that the system can still continue operating even during a fault condition, while the relays and circuit breakers doing their job of isolating or removing the unhealthy part from the healthy part. So, this being the premise of our discussion, let's move into the short circuit capacity assessment. We have clearly understood the aspect of SCR assessment or SCC assessment in the previous few lectures, where SCC is basically the ratio of short circuit MVA, the worst case MVA that can occur during a bolted three-phase fault, divided by the rated MVA of the power network. Now, and more importantly, the short circuit ratio in a way dictates or entails what can be the fault ride-through capability of these inverter-based resources. These inverter-based resources, although being green, have variable injections due to their weather dependency on how much power can be generated. So typically, the SCR value, it would depend on how many such sources are present in the network and where are we trying to estimate the SCR value. Typically, when the SCR location is done near the generating devices, the short circuit capacity is higher because more current can flow from these generators being electrically closer to the fault location. The farther off the SCR location is done from generating sources, the typical fault current contribution is likely to go down. SCR typically depends on the number or type of resources that are present at the point of interconnection. There are different ways of finding the SCRs for different types of resources present. One such common estimation is through weighted short circuit ratio evaluation, which is basically power dependent based capacity evaluation of the short circuit capacity. So PR megawatt I is the rated output of the non-synchronous generator connected at bus I. So basically it's a weighted average of the short circuit ratio from individual point of contribution at the point of estimation. The other possibility is through composite short circuit ratio, where based on the overall SCR evaluation, instead of taking an average rated evaluation, we tend to evaluate SCR at the point of location, considering all generators partially or equally contributing to the short circuit capacity, and then take the ratio with respect to the nominal rating of our inverter based resources. The other well known popular mechanism or index which has recently come up in the last few years is short circuit ratio with interaction factors, where short circuit ratio is basically the rated short circuit capacity divided by the participation or interaction among how the inverter based device can sustain during voltage swell or sag condition, provided it has voltage low LVRT capability in it. So basically this ratio is in a way a estimate of that if the source at node J, the inverter at node J is trying to contribute or sort of respond with FRT characteristic to the fault occurrence, then at node I with some other inverter placed, how much is the voltage magnitude change? That's one way of finding this interaction factor. So basically it is like trying to link the voltage right through capability, or it is basically an assessment of how much the voltage right through capability that can exist for different inverter based resources. All that having said, it all looks good theoretically, but actual problem comes is with the fact that since our inverter based resources are weather dependent, so their injection is uncertain and variable. So during variable conditions where the weather is changing, injection is changing, the SCR assessment is still a challenge. It might also happen that a particular device which is interconnected right now may not be available at a different point of time. So the issue with this is that SCR assessment is a challenge, and then the question comes is, if SCR assessment it's a variable quantity, if it's a challenging factor, how do we decide or dictate upon finding reliable relay and protection equipment settings so that our system can still operate to the extent possible. Moving on to the next aspect of protection schemes or issues in HV systems, high voltage transmission systems. Typical high voltage transmission systems, they are protected by certain philosophies which are known as distance protection, differential protection, and directional overcurrent protection, usually for medium voltage lines. A detailed discussion on these different protection philosophies in itself could be an elaborated course. I'll not go into details of what these schemes are. I'll just cursorily browse through what these techniques are. In addition to these protection philosophies for protecting high voltage transmission lines, these schemes, they have certain elements specified with them. The number codes here indicate those elements. It's again as per some ANSI standard, IEEE standard, which we don't have to bother about as of now. To enable these schemes, we need help of certain elements. Those elements are mentioned over here: distance element, directional protection element, negative sequence protection element, and fault phase identification logic. So basically FID helps in identifying whether actually a fault has occurred in the area of interest, and whether based on this identification these elements should reciprocate or act. Basically these are relays, reciprocate or act to sort of clear the fault. So in terms of distance element, the distance, briefly explaining what the distance element is, it basically tries to evaluate the ratio of voltage sensed by the relay with respect to the current which is sensed by the relay, and basically tries to evaluate the impedance. So basically in case there is a system which is not having a fault, the typical impedance measured by the distance element would be the healthy impedance of the line. In case a fault has occurred, the voltage would tend to go down, the current would tend to go up. That's a typical signature of the typical fault distance element. And what would happen is that during a fault, the distance element may experience a dip in the fault impedance, and that's the overall basis or reasoning of, okay, that a fault has occurred on a particular section of a transmission line. Because of fault, the fault impedance has also come into picture. So overall impedance measured during a fault is less than the actual threshold or suitable value, and hence the corresponding distance element detects that a fault has occurred. So this diagram here essentially sort of indicates what I was trying to say. We have a distance element or a delay present or shown by this square black box, and under healthy condition it would be monitoring the ratio of voltage and current sensed by the relay, and it would typically try to protect the entire length of the line, which is defined by its Z set value. The Z set is usually the positive sequence impedance of the transmission line between bus M and N. In case there is an internal fault, the overall impedance sensed by this relay would be less than Z set, and the distance element would trigger that the fault has occurred. In case there is an external fault, the fault sensed by the impedance sensed by this particular element will be more than Z set, and since it is not designed or it is not supposed to operate, it will try to inhibit operation during external fault. And typical locus of simple impedance relay, we call it as SIR, also in short known as simple impedance relay. If we try to plot the locus of operation of simple impedance relay, which is what is shown by this black box, then Z set is the typical positive sequence impedance of the line, which it should monitor. In case there is no fault, it would still be sensing that same value. In case a fault has occurred, F1 is the internal fault, so it should internally operate, and for F3 it should restrain. So basically this is the locus of the simple impedance relay on RX plane, where the inside portion refers to the trip region for the relay to operate, and restrain refers to external faults. Now, in case we have inverter based resources present in the transmission network, so let's say I have taken a very simple example. I have considered two buses. On one bus I have a synchronous generator or the typical AC grid, and on the other end of the line I have an inverter based resource IBR. If a fault occurs on the line between bus M and N, and I want to see what is the impedance sensed by the relay on the grid side, which is ZG, then since synchronous generator is contributing current ZF, which is marked by the blue line. So if I tend to see this fault impedance ZZ, it would more or less be same as ZMK, which is the impedance of the line between bus M and fault point K. And it would also be encountering or measuring ZF, because IF by IM, this ratio would be more or less equal to 1. Remember, we are talking about a synchronous generator based grid. So fault current contribution would be significantly higher from the synchronous generator side. And typically this, and hence this ratio would more or less be equal to 1. So basically grid side relay will act normally the way it is supposed to operate. The same thing if we try to see from the inverter based resource side, where IN, the current which is being fed to this fault current, is much smaller compared to the current contributed by the grid side because of the protection or internal control philosophy of the inverter. In that case, ZC would be a value ZNK, where ZNK is the impedance of line between node N and the fault point K, with the apparent impedance ZAP. Now, if we talk about this ZAP, which is dependent on this ratio, the fault current IF is significantly higher than IN. In fact, it is almost comparable to IM. IN contribution is much smaller. So this value would be much larger than 1. And for the inverter based side, what we see is that there is an additional factor which is much larger than the actual fault impedance, and hence a large impedance of ZAP appears in. The issue with this operation is that the distance element present near the inverter based resource will basically be seeing a fault which has occurred far beyond the actual location, because ZAP is going to be much larger than ZF, and as a result the impedance seen by the fault distance element would be varying in terms of the current contribution from the inverter based resources. So fault distance is difficult to identify, and the relay may even maloperate with correct settings provided, because the relay would be sensing a fault location beyond the actual value. Coming to our other elements, negative sequence direction elements 67Q, 32Q, typically they indicate the level of unbalance which is present in the system during faults. Ground faults or line-to-line faults, they tend to have this negative sequence element present in them. So 67Q, 32Q in a way helps sensing how much is the unbalance present in the network during a fault operation. And 67Q, it sort of also helps in detecting what is the direction of fault, whether it is an internal fault or a forward fault or external fault, or whether it is a forward fault or a backward fault. And going by the distance element philosophy, 67Q, it again tends to compare or get an assessment of this negative sequence current by comparing the negative sequence voltage and current phasors. So typically in synchronous generator based setup, 67Q would very well be able to compare the ratio of voltages and be able to clearly segregate the reverse faults from the forward faults. Typically the relay which is present on the transmission line, it should be protecting or operating for forward faults rather than operating for reverse fault, because for reverse faults there may be another element present dedicated to it. So basically that's what we call as the reach or set of the relay. So far with no inverters present, all looks good, all looks fine from synchronous generator perspective, because we are able to clearly get an assessment of what is the negative sequence component present in the network. In the presence of inverter based resources, the issue is that inverter based resources not only limit the current quantum contribution, but they also inhibit or provide limited number of zero sequence current or negative sequence current in the network. So the level of negative sequence current, it becomes drastically lower with inverter based resources. As a result, the sensing of this ratio becomes a tricky affair for directional element or negative sequence current element, and hence with this, the issue of negative sequence relay or directional relay not being able to identify the directionality of the fault because of low quantum of negative sequence injection from the inverter based resources during the fault becomes a difficult aspect. So that the overall story is that traditional negative sequence based directional element, they may maloperate during inverter based resources. So what are the challenges in a way from the brief discussion that we had? With inverter based resources, the current quantum contribution is very limited. The fault current angle is also very controlled with respect to the voltage sensed by the relay. There is a lack of negative and zero sequence components in the inverter based resources. So as a result of which, our conventional distance directional based elements, they may find difficulty in correctly deciding whether they should operate or not, and that's where the issue of maloperation comes in. So a possible solution for mitigating these issues with inverter based resources is to not just depend on conventional Fourier transform based relay setting evaluation, which we have not discussed, but those of you who are interested may explore topics or courses on power system protection, where conventional voltage ratio, current ratio are based on conventional Fourier transform or discrete Fourier transform based devices, which does not involve certain sequences present. So the possibility which researchers across the globe are looking around to mitigate these issues due to inverter based resources is to not just depend on conventional methods, but to also expand or look forward to certain signal processing based methods which can help figure out certain good features from the corresponding voltage and current signals, certain machine learning based methods, and obviously other methods which are very well being researched upon or talked about. Unfortunately, I cannot discuss at length about these methods, but those of you who are interested may please explore them accordingly. The last bit is about protection systems for medium voltage or low voltage subtransmission or distribution systems, where mostly the protection philosophy is based on overcurrent protection. Distance element and directional element are there, but they're not so popular, given that the distance element is a expensive device compared to overcurrent protection. So overcurrent protection, what does it do? It essentially compares the magnitude of current with respect to a particular threshold. If the current level is not beyond a particular value, the overcurrent relay doesn't operate. Since during a fault, the current tends to go up. So it's expected that during a fault, current would go up. So overcurrent protection tends to operate accordingly. The overcurrent philosophy may also have directional feature in them. Typical overcurrent relays, from the sake of designing perspective, they are inherently non-directional. So basically, they don't sense what type of current magnitude increase has occurred, whether it's for a reverse fault or a forward fault. In order to make it directional, we have to sense or get an estimate of ratio of the phase angle between the forward current and the voltage sensed by the relay, which helps in indicating that whether the fault is a forward fault or a backward fault. So let's say if I have a transmission or a distribution line where I have the overcurrent relay placed just near the bus, and if I am trying to build in the directionality feature in this overcurrent relay, then for a forward fault, if I draw the phasor diagram, typically for the VR, which is the voltage sensed by the relay, for a forward fault, assuming it's an inductive system, the current would typically be lagging with few degrees of displacement in them. So this is for a forward fault. On the other hand, if I have a backward fault, which the relay is not supposed to sense, then compared to forward current and the backward current would definitely be a very reverse current in a negative sense of IF. So the phase angle differences during forward fault and backward fault are significantly different. And by comparing this ratio, which was also decided or discussed about in negative sequence directional element, the overcurrent relay can get to know whether it should operate for forward fault or not. So it basically helps in increasing the selectivity of the relay. Now, with inverter-based devices or resources present, the fault current contribution from the inverter-based resources do create their own issues. So one such example of relay blinding is shown over here. What is shown is that a fault has occurred on this particular section of the fault, and since inverter based resources do not contribute much of current to the fault, majority of the fault current contribution is happening from the grid side. So what would happen is that, it might happen that for a fault which has occurred on this particular section, because of the electrical distance closeness of the fault location to the inverter based resource, the current contribution of IBR may be higher compared to the physical distance location of the grid side from the fault location. So basically, it might happen that IBR may be lesser or may be more than the grid current, and as a result, the relay which is supposed to operate, since it is not sensing much of change in the fault current contribution from the grid side, this relay is essentially blinded to the fault location. And this is typically going to happen when the IBR or the fault point is much closer to the IBR point. Maybe it is a non-serious fault like single line to ground fault, where the current differences is not highly different from the normal load current, and the grid location is far off from the actual fault location. The other aspect which may happen is the case of false tripping, where a fault has occurred over this particular section of the network. The grid is also contributing to the fault. The inverter is also contributing to the fault. So ideally speaking, the relay that should clear out the unhealthy part is the relay marked marked in enclosed here. The relay present near the inverter based resource should not operate because the fault has not occurred in its own section. But because of current contribution from the inverter, the relay may also operate. And the last part is coordination issues. There are dedicated primary and backup pairs assigned for relays. So if primary relay doesn't fail to operate, backup relay should take up the chance of operating. And this sort of issue also comes up because of bidirectionality flow of power or current from the inverter based resources. So in a way, to sort of summarize, similar to high voltage line protection, low voltage line protection also has the similar aspects because of the current contribution from the DGs. Intermittent power generation may lead to relay coordination issues. So the suggestion still remains the same. In order to cater to these challenges, one has to look for non-conventional based methods like machine learning based methods, data driven based methods, or feature extraction based methods, which can help easily identify the signatures which come in because of inverter based resources or distributed generators. So that's all for the fault analysis part. Next lecture we will start with our last module, which is stability analysis. To be precise, stability analysis again in itself is a very vast voluminous subject. We would specifically be talking about one specific stability analysis problem, which we call as transient rotor angle stability analysis. The other stability analysis problems we will not discuss or understand at length. But the next lecture, we will just go through the basics and understand the different stability problems that might come up. Thank you.